the generalized inverse. Here first, generalized linear model. And what is the condition for the generalized linear model such that our matrix A have the form m cross n, where m and n are different, and the inverse will exist when the determinant of this is not equal to 0, and the model should have this criteria where G is the inverse, so A inverse of A and then multiplied by A should be equal to A. So this is the criteria of determining your generalized inverse. For this type of matrix of this format, we can find another way or another notation to solve this kind of matrix. And here I would like to mention that the generalized inverses, they will be unique when the column rank of the matrix A is equal to n is less than m. So this condition should be satisfied, then your generalized inverse is unique. There can be some conditions when your generalized inverse may not be unique, but it will exist. So there can be some solutions of your matrix such that the inverse may not be unique. So we'll discuss one example of that. So what is a generalized inverse? It is a way of finding the unknown, finding your regression coefficients in this example, where the rank of the dimensionality of your matrix is not of the form n cross n, rather m cross n. Let's look at the example first. Let's suppose we have a matrix A which is represented and its size is 1 cross 2. So it's generalized inverse is a matrix G xy which are the same form, rows 2 into column 2 into cross 1, which satisfies AGA should be equal to A. So we can represent this as matrix A we have here. Then what about AGA? G is here the new inverse that we are going to have. So it will be 1, 2 or original matrix. Then we will have a generalized inverse xy, and then we again multiply it by 2. So the form that we have here becomes So what about the generalized inverse? So there are two possibilities. Now we don't have a single unique inverse. Rather, we can use either put x is equal to 1 and y 0, and we get matrix A 1 2. Okay, now what about 3 and minus 1? Again we put the value of x and y, and our matrix A is 1 and 2. In this equation, put the value of your x and y's. It's 2y, x plus 2y. So 3 plus minus 1 into y, and y is minus 1. And then we put the value and we get this to the same matrix. So the the point here I'm trying to make is that your generalized inverses, they may not be unique, and they will only be unique when the column rank of your matrix A is equal to column rank of A is n is less than n. If this condition is satisfied, then your generalized inverse is unique. Otherwise, it can have multiple inverses for the same matrix. So let's see. We put in the value of here. So we can have two generalized inverse for the same matrix A. Let's suppose G is 1 and 0. So 1 plus 0 and what do we get? X plus 2y or matrix A. Then we put the value of 3 and minus 1 in the same equation. 3 plus 2 times minus 1 is again 1 multiplied by 1 and 2, and we get the same matrix. So one matrix could have more than one generalized inverse. So this is the concept of generalized inverse, and if you want to further study, you could get and study the content from linear algebra topics, and if it's still not clear, then we can discuss it further. So now our matrix is represented in this format, and I will tell you how do we get these equations. We now know that we can get this matrix A, and it can be represented in this way, and your B matrix can be represented in this way. So we will study how these matrix representation, mathematical representation are possible, although you might find it very basic, but still I would like to put some thought into this. So what about if we are given a matrix X and we take the transpose of this matrix? So X transpose will be change the rows, the columns into your rows. 1 0, 2 0, 3 0, 4 0. What about the next column? 2 1, 2 2, 2 3, and the last one is D. Yeah, 1D. Okay. So in this form we have your X transpose, and the X we had was 1 0, 2 0, 3 0 up to 1D. And then if we multiply this with this, first term will be 1 0 1 0 plus 2 0 2 0 3 0 3 0 and so forth, 1D to 1D. And this is your first term for the matrix, so with a comma. And how we can represent this? Summation of I naught, where does I start? From 1, and where does it end? T. Then we will have the next term, which we can see 2 1 2 2 2 3, and the X matrix can be represented. This I remains the same, but your second index changes from I1, it remains the same. So I0, I1, I2 up to ID. So this is how we can represent. I have shown you only this term. We can find X transpose of X and how we come up with this term. So another way of solving your generalized linear model is that you take the transpose, then multiply it by X, then take the inverse. This will be your new type of matrix representation, A inverse, and then we have your transpose of Y to finally come up with this, where 1 in the first column represents your intercept terms as we solve any matrix. If you still are not clear and you have difficulty, just visit the matrix and inverses to solve the unknown variables, and it will be much clearer to you. Just a short 5-minute revision will bring you back to the track. So now, giving these data points and using these data points, we can, this is your value of X and this is value of Y. This is the scatter plot as it is represented over here, and Y, this is f of xy, which is your regression line. And since we have only one variable, so this will be your W0, this will be W1 X. So your line is this. And then using basic calculations, you come up with your intercept value and the slope, and this becomes your regression line. You could solve this with and practice this solving with MATLAB or Python as an exercise. And if you have not already studied Python, it will be a good exercise to understand the structuring and representation of your code or script in Python. So it is a good advice that you implement the generalized inverse of a matrix representation and solve this problem that is given, and we already have given you the solution, so you can check the results also. Now we come up with the additive linear models. Additive linear models, the generalized version of linear regression, which I am talking about already. So this is, we are moving from the linear regression, in this lecture we are moving towards the generalized version of the linear regression. So in this case we have the different predicted variables, and f of x is determined, and this was the equation that we had, W0 summation of wj xj, and we intended to find the best fit line for this given data. So how do we generalize this? We represent or replace your variable x with a predetermined function. Instead of x, a variable, we can have a function of x. So this function performs some transformation to your x variable to give you a representation of your data. Some variables could have a linear relationship and some could have a quadratic relationship. Means your data is better represented as a linear relationship, or your variables could have polynomial representations. So in this case, we replace your x with a function of x. If your data is represented in a sinusoidal form, we could represent a sine of x. So this predetermined function h of x is replaced in this equation. Rather, we could see that this h of x could be also cover or consider linear regression variable form, where h1 of x could be x, h2 of x could be x2, hd of x, xd could be xd. Of course, multiplying factor w2, w1, w1, x1 multiply, okay, yeah, there. So xd, wd. So this is the generalized form, we say, and one of the representation of this generalized form is the linear regression equation. So replacing your variable x with a predetermined function x. Linear regression is represented where h1 of x is x1, h2 of x is x2, and hd of x is xd. Yeah, so don't multiply. We have h of x replaced with the variable and w2 is multiplied with this. And h1 of x is x1 and w1, the slope, is multiplied with this. So how do we represent polynomial regression as I talked to you? So one of the function h of x could be in the form of x square, it could be in the form of x cube, it could be in the form of square root of x, it could be in the form of sine of x. Depending on our data, what kind of data we have. We have a periodic data with the sinusoidal curve, so use the sine function. That's why we choose the h function depending on our structure of our data. Sorry. So here they represent polynomial regression of second order, w0, h1. So we can also represent it in this form. h1 simplified, h2, h3, h4. I'm just going to explain this, how this is happening. So from hd, for example, d equal to 4, we have d variables, so we have d equations, we know that. So d is 4, so this one is d plus 1, and the second will have 2d, then 2d plus 1, h2d plus 1, and finally what we will end up is hd square plus d. So it will be h of 20. The last variable we will have in the system of equations will be h of 20. This is the representation of polynomial regression, and the same data we have, we can see here the same example, but this is your polynomial representation where your h1 of x is x, h2 of x is x square, and h3 of x is x cube. Now you see that the line has, because it is third order polynomial and we have two curves, so in this data it is not a linear form, rather it is a curved representation. And then we have the equation f of x w0 plus x w1 x1 plus w2 x square plus w3 x cube up to variable x cube. And then solving this, we had a curvature line. Next, what about if we try to fit a sinusoidal? Maybe it is sinusoidal or data. In this case, we only have 10-12 examples. But our machine learning algorithm that would be working with, it could have a large number of samples. 1,000K or 1 million samples, 2 million samples, 100 million samples. So in this case, we cannot visualize our data in this form. So we don't know how the data visually is represented. So we should have some understanding of our data before we consider our function h of x. So in this case, we are choosing the function sine a of x. So each variable will have an independent relationship with this f of x. So for the linear part, for example, when x is linear, it will have something like this, relationship like this. But if it is sinusoidal, it will have like this. And then we combine both of them, it becomes and appears like this. And w0 will determine the point in which is the intercept when x is 0. What is the value of y when x is 0? So we are combining these two linear and then the sinusoidal representation, and then combine to finally get this kind of curve. In the additive linear model, in general, I want to put some thought into this. So in the additive linear model, we are adding the functions h of x one by one, and there is no interaction between the variables x1 and x2. There is no interaction. We consider and we assume that there is no relationship among the variables, and each of them have an independent effect on our function f of x. So this is we have to keep in mind. So now our function f of x is represented in this format, where h first value is 1, h0 of x. Now we take the derivative or the partial of this function to minimize. Then of course we will have this kind of representation. If we did not start with h0 of x is equal to 1, then we would have for j0 and then j is greater than or equal to 1. But now we have adjusted that. So we have in this format, we have already adjusted. So we have 2 times the multiplier term and the function. And then we represent this. When do we minimize? When it is equal to 0. Each term is individually put equal to 0. So we are going to represent them as equations. Simply we are here replacing x with h0 of x. And in matrix form, it can be represented like this. Replace your x with h, function of x, hx. And then using the generalized inverse, we can find the value of regression coefficients, w. It can be represented, first we have x0, now we have in the h function, we have a function, each of them, this is function x, this is sine of x, maybe this is x square, x cube, so each is a different function. And using the order 3, we now solve this polynomial regression and the same example, and the curve that we get is in this format. So sinusoidal plus the linear did not fit well, but if we consider the polynomial regression, it looks and appears as a better fit for this data. So this two things. We can have a better fit of the model when we have the understanding of our variables. What is the relationship individually of each variable with your function f of x or your y prediction or estimated y? If we understand that better, then we can design or best fit model to better represent our data. And the better fitting our model is, the better we are at predictions. Y hat. The better we are at predictions, y. So y f of x minus yi, in this one we say expected value of y. Okay, for the sinusoidal fitting of this model, if we consider our data is periodic, it is represented in this format. Another way in which we can represent the functions h of x are smoothing functions. Again, the choice of this function depends on the representation of our data or the pattern in our data. Here we are choosing a kernel density function, where we can see that the translation of each of them is different, but we can see at the bottom we have the same value. So this data essentially is distribution like this. A normal distribution we have our data. It is represented like this. Sorry. Our normal distribution of our data, it is represented by this, where this is the mean and this is, and our data can be represented like this. So this one has translation of -1, a slightly skewed version. Then the next one has more skewed, and the last one has greater skewness. And the final outcome is or. So this one is represented like this. This is the visual presentation of for each function, h of x function. And final model, or the final best fit line that we get from the kernel density function, is this red line. So in this lecture, what we have studied is how we can how we can have the simplest approach for linear regression. What is multiple regression? Then there are different approaches other than this. Then we studied the polynomial regression. Then we converted into generalized form of linear regression. We studied the generalized inverses, and using that we've studied the additive linear model, where each h of x is added to the function such that there is no interaction between the any two variables, and each one has a separate effect on your model, best fit model, and then sum them up to find the overall best fit model. The other approaches, and then of course, the kernel density estimation. So smoothing functions can also be used. So the Gaussian function we can use, which has normal distribution. So there are some other approaches to solve the linear regression. We have the gradient descent approach, MLE approach. Both give the same solution as your SLE, solving linear equations. So we converted our problem into a system of linear equations, and then we solved it. Either it was using generalized or additive linear model, or the basic polynomial, or the linear regression model. So we know that all of them are very famous. Both of them are very famous. I'm talking about the gradient descent and the MLE. So, and they are useful. And why do we study? Because they are useful and important methods to solve problems in machine learning domain. So we'll focus on the gradient descent method in our next lectures. That's it for the linear regression concept, and I hope some of the confusions I have addressed them in this.